Hi, welcome to this lecture on modules and clients. Here's the outline for the lecture. We'll first talk about the distinction between a module and a client program, and then we'll discuss how you use functions defined in a module inside of a client program which makes use of that module. And then we will talk about modular programming abstractions, and then we will discuss three examples of modules. One module which can be used to compute with random numbers, another module that can be used for list processing, and then a module that can be used for standard statistics. Now, using this idea of modular programming, we can not only divide a program into functions, but we can also keep them in different files. Now, we distinguish between two types of Python programs. These are modules and clients. A module is a program that contains functions that are available for use by other programs. For example, math is a module. So that's a good example to keep in mind. And the functions that you have in this module are mathematical functions such as sine, cosine, and so on. And then a client is a program that makes use of functions from a module. So an example of a client program would be the quadratic program that we talked about in an earlier lecture. So quadratic.py, because that's a client program of the math module. It makes use of a function sqrt from the math module to compute the square root of a number. So that's what a module and a client program is. So let me repeat, a module is simply a program that contains functions that are available for use by other programs, and a module is not run as a standalone program. So that's something to keep in mind. Whereas a client program is something that you run as a standalone program, and it makes use of functions defined inside of a module. Okay? So math is something that you don't run as a standalone program, but quadratic is something that you do, right? And quadratic does make use of the math module. Now, there are 5 steps involved in creating and using modules. In the client program, if you want to use a certain module such as math, you need to first import it. Okay? And then in the client, when you are trying to use a function from that module that you imported, the way you use that function is by qualifying the name of the function with the module. All right. So for example, if inside of your client program such as quadratic.py, if you're importing the math module in order to use the sqrt function, the way you call the sqrt function is by saying math.sqrt of some number such as 5. Right. So this is what we mean by qualifying the name of a function. You put the name of the module first, and then a dot, and then the name of the function itself, followed by any arguments to the function. Okay, so that's step 2. And then in the module itself, what you need to do is you import you implement the functions that are part of the module, and then you also write what is called a test client. Right? And the purpose of the test client is simply to test the functions that you have implemented in the module. All right, so this is what you do on the module side. You first implement all the functions in the module, and then you write a little test client, which is essentially a main function. And we'll talk about this later. It's a function that tests the implementations of your functions inside of that module. Okay, and then in the module you also eliminate arbitrary global code. So it's always a good idea to avoid global code if possible. Okay. And then finally, you need to make the module accessible to the client so that the client can use that module and call functions in that module. All right? So these are the steps that are involved in creating and using modules. On the client side, you need to do these two things, meaning import the module that you want to use and call the functions from the module by qualifying them as such with the name of the module. And then if you're the one who's implementing a module, then you need to implement the functions that are part of that module and then write a test client that tests the implementations of those functions, and then try and avoid any global code, and then finally make the module accessible to the client, right? To the users who want to make use of that module. Now, modular programming has many advantages. It enables us to independently develop and debug functions for an application and then utilize them at a later time, right? So that's a big advantage that modular programming allows you. Now, user-defined modules are files that each contain a set of related functions for use by other programs. All right. So, for example, let's take std random. Okay, so this is a user-defined module, and by that we mean it's a module that's not part of the core Python library, but this module is actually written by the authors of our text. Now, what does this module contain? Well, it contains a set of related functions for use by other programs. And what are these functions? Well, these are functions that you use to compute with random numbers. Okay, and let me give you another example, std stats. So we're going to look at this later on. So this module contains functions with which you can do basic statistics. So this is also a user-defined module. It's not part of the Python core. Okay. And then there are other modules that we have already seen, std draw, std audio, okay, and so on. All right. So these are all examples of user-defined modules, and they all contain, and each of them contains functions which are related. Okay, so this one contains functions to work with random numbers. This one contains functions to do basic statistics. This one here, std draw, has functions with which you can draw something on the screen, and then this module here contains functions with which you can do audio processing. All right. And so in this lecture, we are going to talk about these modules, std random, std stats, and in addition, we will also talk about std array. Okay, so we're going to discuss these three modules in considerable detail in this lecture. Now we're going to use three abstractions to manage the process of developing user-defined modules, such as the ones that I just talked about, like std random, std array, and std stats. Right? What are these abstractions? Well, the first abstraction is that of an application programming interface, or API for short. And this is something that we've already talked about. So what is an API? It's a table that has two columns. The first column simply lists the functions that are supported by the module, and the second column lists a short description of those functions. So here I'm showing you the API for a module that we've talked about before, that defines two functions, the Gaussian PDF function and the Gaussian CDF function. Okay, so these are the names of the functions along with the arguments, and these are the short descriptions for those functions. Okay, so this is what a client needs to know in order to use this module. The client doesn't care how these functions are implemented. Okay, if the client needs to calculate the CDF of a set of arguments of a Gaussian function, then the client simply needs to know the name of the function and the arguments for the function. Okay, and with that, the client can make a call to the function as such to calculate the percentile score, right, or the Gaussian CDF. So that's what is shown here. So this is the other abstraction. In the client program, you make use of a function from the module, Okay, so here is the API for the module. Here is the client program or a part of it that makes use of a function from that module, okay, to calculate the percentile score. So let me emphasize this point that in a client program, that uses a certain module, such as the one shown here, you only need to know the API for that module. Okay, you don't need to know how the individual functions are implemented. All right. Okay, and then the last abstraction is that of implementing a module. So if you are the person that is responsible for implementing this API, meaning implementing this module, then you need to actually flesh out the implementations of these functions. So in that case, you need to worry about how these guys are implemented, okay, because you're the one that is going to implement it. So that is what is shown here. So inside of some file, some Python program, you will simply implement the functions from the module. Okay, PDF is this function here, and CDF is this function here. And in here, in the body of the function, you'll have the appropriate code. Right? And the code for this is something that we have seen before, the code for PDF and that for CDF. Okay? So we know what a module is, we know what a client program is. What is a library? Well, a library is a collection of related modules. All right. So for example, there is a very famous library in Python called NumPy, and that's basically a library for scientific computing. All right. So if you want to write programs that involve scientific computation, then you would make use of this module called NumPy. So what is NumPy? It's a collection of modules that are related to scientific computing. All right. Now, a private function inside of a module is a function that has its name start with an underscore by convention. Okay, that's how you tell that a function is a private function. So you simply use a certain convention, and a convention that we are going to follow is start the name of that function with an underscore. Okay, and a private function is essentially a helper function, okay, that is not intended to be called directly by clients. So private functions are not even listed in the API, so the client doesn't know about these functions. Their only purpose is to serve as helpers to other functions that are part of the API. Okay, and a private function again has its name by convention start with an underscore. So here is an example. So the first function that you see here is a private function because its name starts with an underscore. So it's underscore phi, and it takes an argument x. So what does this function compute? Well, it computes the standard Gaussian PDF. So phi of x, recall, is simply this formula, e to the x square divided by 2, the whole thing divided by square root of 2 pi. So that's what the private function computes. And then this function here, which is not private, it is called phi, it is part of the API. Okay, it's part of the API that we just saw in the previous slide. And what does this function compute? Well, this computes phi of, it computes the Gaussian PDF, okay, with a certain mean and standard deviation. So this is x, mu, and sigma. Right? In this case, mu and sigma were simply 0 and 1. Right? Whereas here, it's arbitrary mu and sigma. So this is simply calculated as the phi of x minus mu divided by sigma, and this whole thing is divided by sigma. Okay, so notice that this phi refers to this phi which is defined right here. All right, so this guy makes a call to this guy, which is what is defined here, right? And that's what you see in the implementation. So this phi, which is that, right, makes a call to this underscore phi, which is that, right? So that's what is defined here. Okay, so as you can see, this underscore phi, which implements this guy here, is simply a helper for phi. the client doesn't even know about this function. It's not part of the API. All right. So what if, so that's why, this function, which is part of the API, provides a default value for mu and sigma. So what if the client wants to actually compute the standard PDF where mu is 0 and sigma is 1? Well, in that case, the client would call this function phi from the API, not giving the second and the third argument, which default to 0 and 1, okay? Which is basically computing the standard Gaussian PDF. Right? Okay, so that's what a private function is, and notice that in Python, even if a client goes about calling a private function, the Python does not restrict the client from doing that. All right, so you typically don't advertise private functions inside of the API, but if the client discovers it somehow, the client can call those functions, right? And Python is not going to stop them from doing that. But that doesn't mean that the client should call private functions directly, right? So it's a good practice to avoid calling private functions. Right? In other languages, these are checked by the compiler. So in Java, for example, functions that are denoted private cannot be called by a client program. Right? The compiler will object to that, whereas that's not the case in Python. Now, how do you document a module? So to document a module and the functions that are part of the module, you simply embed the documentation string inside of triple quotes. So you have triple quotes such as that, and then you put your documentation string, and then end it with triple quotes. Right? So here is an example. So here I'm showing you the Std random module, which we're going to discuss soon. And here what you see at the very top is the documentation for the module itself. So we mentioned the name of the module, which is stdrandom.py, and simply provide a short string that tells you what that module is all about. So it says that the standard random module defines functions that are related to pseudorandom numbers. Okay, and notice that the documentation string has been embedded in triple quotes. So that's the module level documentation, and then inside of that file stdrandom.py you have the functions that belong to that module. Okay, and here I'm showing you just one function, which is called uniformInt, and that simply returns a random integer from the interval low to high. Low is inclusive, high is not. And here is the documentation for that function. Okay, again notice it is embedded in triple quotes. And what we're saying is that the function returns an integer chosen uniformly at random from the range low to high. Okay, so this is how you document your modules and the functions inside of modules. You simply embed the documentation string in triple quotes. So what we're going to do next is look at 3 different modules. We're going to look at standard random, which defines functions that you can use to work with pseudorandom numbers, and then we will talk about standard array, which defines functions for list processing, and then finally we will discuss standard stats, which is a user-defined module that defines functions for doing basic statistics. All right? And in each case, we're going to look at the 3 abstractions, all right, that we talked about. So the first is the API for that module that we are currently considering. Okay? And then we will look at a simple client program that makes use of that API to solve some interesting problem. And then finally, we will discuss the implementation of the module itself. Okay? So for each of the 3 modules, we're going to consider these 3 abstractions, namely the API for the module, a client program that makes use of the module, and then the implementation of the module itself. All right? So let's start with our first example, which is a user-defined module for working with pseudorandom numbers. So this module is called stdrandom.py or stdrandom, and here is the API for that module. Okay, so let's walk through at least some of the functions here. So the first function called seed is what you use to seed the random number generator with some number I. Okay, and this is something that you don't have to do because it's done by default. But if you want to get the same sequence of random numbers again for debugging purposes, then you would seed the random number generator with the same number. All right. So for example, in 2 different runs of a program that makes use of std random, if you seed the random number generator with the same number, let's say 42, then when you run the program and when you ask for a sequence of random numbers, you're going to get exactly the same sequence, right? So if you're trying to debug a program that has a random element to it, and if you want to generate the same sequence across 2 runs, you want to seed your random number with the same number. Okay, but again, this is something that you typically don't do because the random number generator is automatically seeded with a random integer. Okay, the next function is called uniform hint, and this returns a uniform random integer in the range low through high, where low is inclusive and high is not. So for example, if you say uniform int 1 and 7, then that is like simulating the roll of a 6-sided die. Okay. Uniform float is a function that returns a random float in the range low through high. Again, low is inclusive, whereas high is not. Bernoulli is an interesting function. It takes a probability p as an argument, and it returns true with that probability p and false with probability 1 minus p. So if you were to simulate a coin flip using this function, a fair coin flip, then you would call this function with the argument 0.5. So in that case, it's going to return true with probability half and false with probability half. Binomial is a function that takes 2 arguments, n and p, and it simulates the flip of n coins which are biased to an extent p. Okay, and it simply returns the number of heads that occurred. So if you call this function with arguments 10 and 0.5, then what it does is it simulates 10 coin flips. Each one is a fair coin, so that's why the second and that's because the second argument is 0.5, and it simply returns the number of heads that occurred, right, in those 10 flips. Gaussian is a function that returns a Gaussian PDF, okay, which has a mean mu and standard deviation sigma. So this is like the PDF function that we talked about before, right? Then discrete is a very interesting function. It takes a list as an argument. So this list could be, for example, 0.1, 0.3, and let's say 0.6. Okay, so a list with 3 arguments, a list with 3 elements, 0.1, 0.3, and 0.6. What discrete will do is it will return the index of these elements with probability given by the value at that index. Okay, so what are the indices here? Well, it's 0, 1, and 2. So a call to discrete A will return the index 2 with probability 60%. It will return the index 0 with probability 10%, and it will return index 1 with probability 30%. Right? So that's how discrete works. So if you make 100 calls to discrete with this list as an argument, then roughly 60 times you're going to get the number 2, the index 2. Roughly 30 times you're going to get the index 1, and roughly 10 times you're going to get the index 0. Okay, it's a very interesting function. Shuffle is also a very interesting and useful function. It takes a list as an argument and simply shuffles it in place using an algorithm that we discussed in class. And then finally, this function exp, what it does is it returns a float from the exponential distribution, okay, with parameter or rate lambda. Okay, so that's the std random module, and remember that the way you use this module is by saying first you import the module, so you import std random, and then so let me write that. So import std random, And then if you want to use some function, let's say Bernoulli, you would simply say something like some variable x equals std random dot Bernoulli and some argument, let's say 0.5. Okay, so it's the name of the module dot the name of the function and then the arguments. Okay. So now let's look at the next abstraction, which is let's look at a client program that makes use of the std random module. Okay, and this client program is going to do something interesting. So the program is called std random client.py, and it takes a command line argument called trials as an integer, and it simply plots trials number of xy points to standard draw. Okay, where x and y are obtained from a Gaussian distribution. Okay, and this Gaussian distribution is going to have a mean which is 0.5, and it's going to have a standard deviation which is 0.2. Okay, so x and y are going to be drawn from this distribution, and how many such xy pairs do we draw? We draw trials number of xy pairs, and we simply plot those xy points on the screen using the std draw module. Okay, so let's go through the program. We first import std draw, and then we import std random, which is what we just talked about in the previous slide, and then we import sys. And then we get a command line argument trials as an integer, and then we set the pen radius to pixel width, so that's the 0.0, and then I goes from 0 all the way up to trials minus 1. So we are performing trials number of iterations, where each iteration involves getting an x and a y from a Gaussian PDF whose mean is 0.5 and whose standard deviation is 0.2. Okay, so that's the mean and that's the standard deviation. Okay, and how do we do that? Well, we make a call to the Gaussian function from the std random module. Okay, so this was a function in the API of std random, right? So we get an x from Gaussian PDF, we also get a y from a Gaussian PDF, and then once we have xy, we simply draw it on the screen by making a call to the point function from std draw module. Okay, so that's simply going to draw the point xy on the screen. And then we repeat this process for trials number of times. And then at the end, outside the for loop, we show the canvas. Okay. So when you run this program with the argument 100,000 for trials, what you see is a screen like this with 100,000 points in it. Okay, and these the xy values for these points, the x and the y values, were drawn from a Gaussian distribution. Okay, so that's why whose mean is 0.5 and whose standard deviation is 0.2. Okay, and what is the scale of the canvas? Well, we didn't set it explicitly, so in that case the scale defaults to 0, 0 and 1, 1. Okay, so 0.5 is smack in the middle, so that's 0.5. So that's why you see this blob in the middle. Right, so the xy values are picked from a Gaussian distribution, and the y values are also picked from a Gaussian distribution. Right, whose mean is 0.5, and whose standard deviation is 0.2. So that is standard deviation, right? Same here. So from here to here, standard deviation. Okay. So that's a nice little client program that makes use of the standard random module to do something interesting, namely plot these pairs, xy pairs, on the screen where x and y values are obtained using the Gaussian function from the std random module. So the next thing that we're going to do is look at the third abstraction, which is how you implement this module. So if you were to implement std random.py, how would you implement its API? So that's what we'll discuss next. So here is the module, right? std random, an implementation of the functions from the API for std random. So this module is a random number module that defines functions related to pseudo-random numbers. Okay, so let's walk through the implementation. So we first import random because std random is going to use Python's random module to work with random numbers. So std random is essentially a wrapper for random, right? It makes use of the underlying random module from Python, and on top of that it defines a whole set of user-defined functions. Okay, so std random provides a much richer API than random itself, right? But at the heart it uses Python's random module. And then we import math, and then here is the very first function from the API, the seed function. Okay, so the seed takes a single argument I, which defaults to none, and seed simply makes a call to seed from the random module to seed the random number generator with the value I. Okay, so we simply delegate to the underlying to the random module from Python. Okay, so that's seed. What about uniform int? So uniform int is supposed to return a random integer from the interval low through high. But here again, we can simply return whatever random.randRange returns with the arguments low and high, because randRange does exactly what uniform int is supposed to do. So here again, we delegate to random.randRange. Right? So you might ask, like why even bother with this exercise? Why not simply use random.randRange? Well, that is because std random is not just like a copy or a mirror of the random module. It implements other functions as well. Okay, so it makes sense to provide support for the ones that random supports, and in addition provide other functions that might be useful inside of a client program. Okay, and so that's one advantage of working with std random, because you get a lot more than what you get from random, in addition to what the stuff from random. And then you also have better names, in my opinion, in std random. So uniform int makes it very clear that this function is returning a random integer picked uniformly at random from that interval. Okay, so all right, so that's uniform int. What about uniform float? So here again, this function is supposed to return a float, a random float from the interval low through high, low inclusive, high is not. But that's exactly what uniform does from the random module. So here again, we simply delegate to random.uniform with those arguments low and high, and return whatever random.uniform returns, right? What about the Bernoulli function? Well, this is something that is not available in random. It's a very useful function, but it's not available in random. So how does its implementation work? Well, it's pretty straightforward. We take an argument p, which defaults to 0.5. Okay, so if p is not specified, it defaults to 0.5. And then remember, what is this function supposed to do? It's supposed to return true with probability p and false with probability 1 minus p. So how do we implement it? We simply call random.random, which returns a number between 0 and 1. Okay, and we compare that with p. If it is less than p, this expression returns true, and if it is greater than or equal to p, it returns false. And that's exactly what we want. We want to return true with probability p and false with probability 1 minus p. Okay, so that's Bernoulli. What about binomial? So binomial, recall, simulates n coin flips, where each coin is biased by that value, p. So p defaults here again to 0.5. Right? And what is binomial supposed to do? It's supposed to return the number of heads that you get by flipping n coins, each biased by p. So the code is rather simple, but quite interesting. We create a variable called heads and set it to 0. So that's simply going to count the number of heads. And then I goes from 0 through n minus 1, because we need to perform n coin flips. And how do we simulate a coin flip? Well, we simply call Bernoulli, okay, which is this guy here. So this Bernoulli is a call to this guy, giving it an argument p, okay, this fellow. And that's going to return true or false. And if it is true, we simply increment heads by 1, because Bernoulli p, if it returns true, that corresponds to heads. Okay, and then outside the loop, we return heads. Alright, so it's a very nice implementation where we make use of another function from the very same module to get the job done. Alright? Okay, the next function is Gaussian. So that's supposed to return a value sampled from the Gaussian distribution whose mean is the first argument, and whose standard deviation is the second argument. Okay, so here it's very easy because the random module from Python supports a function called Gauss, which does exactly that. Right? So we simply call Gaussian with the arguments mean and standard deviation. Okay? So this here actually is a typo, so this should be mean, or this should be called mu. Okay. So we simply delegate to the Gauss function from random, giving it the arguments mu and sigma. Okay, let's keep going. The next function from the API is discrete. So remember, discrete takes a list A as an argument, and what it's supposed to do is return an index I with, so return I with probability A at I. That's what it does. Okay, so how do we implement it? Well, we first get a random number, a random float between 0 and the sum of the values in A. So for example, if A contains that list that I mentioned before, 0.1, 0.3, 0.6, what is the sum of A? Well, it's 1. So in that case, R is going to be a random number between 0 and 1. Okay. So here again we make a call to uniform float, which is a function that we just discussed in the previous slide. Okay, that's also a function that's part of std random. Okay, and then we initialize this variable called subtotal to 0. So R is going to be, for this example, a number between 0 and 1, subtotal is set to 0, and then I goes from 0 all the way up to length of A minus 1. And then we simply add A at I to subtotal. So initially 0.1 is added to subtotal, so subtotal is now 0.1, and then you compare subtotal with R. So if subtotal is greater than R, you return I, the corresponding index. Otherwise you keep going. You take the next value, add it to subtotal, compare it with R, this random number, and if it is greater you return I, otherwise you keep going. Okay, so for example, let's say for the sake of argument that R came out to be 0.27. Okay, so initially subtotal is 0.1, it is not greater than R, so what do? You add the next probability 0.3 to subtotal, so that now becomes 0.4. So now you compare 0.4 with 0.27. Well, it is greater, so you return I. And what is the value of I now? Well, it's 1. So in this case, you end up returning 1. All right. Okay, and I hope you guys see the similarity of this implementation with something that we saw before. This is basically the roulette selection method. Roulette selection method. And where did we see it? We saw it in the PageRank case study. Right? Okay, what about shuffle? Well, shuffle is extremely straightforward. So shuffle is supposed to take a list A as an argument, and it's supposed to shuffle those elements in place. Well, random has a function called shuffle that does exactly that. So we simply make a call to random's shuffle function, and we give it that list as an argument. Okay. And notice here we don't return anything. So shuffle doesn't return anything. Even random.shuffle doesn't return anything. But it has a side effect, which is to sort that. Sorry, not sort, but to shuffle that list. Okay. So that's that. And then the last function in the API is the Exp function, which is supposed to return a point from an exponential distribution with that rate. So here we simply implement it as this formula. So that's the formula for an exponential distribution with the rate lambda. So we simply return that, right? So it's minus ln of 1 minus some random number, let's call it r, which is what is obtained by this call, so that's r, and the whole thing is divided by the parameter or the rate lambda. Okay, so that's what we're doing there. All right, and then the last bit is the test client. So this function that you see, the main, is the test client that we discussed earlier. Right? And what's the purpose of this test client? Simply to test the implementation of all the functions that we have implemented in this module. Right? And that's what you see. The test client simply imports some modules, sys and stdio, and notice that this is done inside of the test client itself. So the module itself didn't need sys and stdio. We need this module only for the test client, so we just import it locally here, right? And then the random number generator is seeded with a fixed number 1. So whenever you run this program, you're going to get the same sequence of random numbers, right? And then we get a command line argument n as an integer, and then what the program does is, what the function does is, it simply does n iterations, and in each iteration it makes calls to functions from the module: uniform int, uniform float, Bernoulli, binomial, Gaussian, discrete, and so on, with these arguments. Okay, and simply prints the results out. So again, the purpose of the test client is to simply test the implementations of the functions in the module. All right, and this test client is not advertised in the API, so it's a private function, and hence the underscore in the name. So main starts with an underscore in its name, meaning that it's a private function. Its purpose is only as a test client. Right? So, and then we have the standard line here that says, if name is that, call the test client. Okay. So on the command line, if you run this program stdrandom.py, then the test client is invoked, and you essentially test the module. Okay, but this module is typically not run as a standalone program. Instead, it is imported inside of client programs. All right. Okay, so that completes the implementation of the Std random module. Now let's look at our second module, which is Std Array. So here again, we're going to follow the 3 abstractions that we talked about. So we'll first look at the API for the module, and then we'll look at a client program that makes use of the module, and finally discuss the implementation of the module. Okay, so here is the API for the Std Array module that you can use for working with lists. So let's go through the functions in the API. So the first function, recall, is a function that you can use to create a one-dimensional list of size n with the values initialized to what is given as the second argument. Okay, so this is a function that we are familiar with, create 1D. Create 2D creates a two-dimensional list that has m rows and n columns with all the values initialized by that value, right? And then these functions, write 1D and write 2D, what they do is they take lists as arguments. So 1D takes a one-dimensional list, 2D, write 2D takes a two-dimensional list, and simply writes it out to standard output. Okay, so very convenient functions that you could use to write an entire list out using a single function call. And then this function here reads from standard input. It reads a one-dimensional list of integers from standard input, and then this one here reads a two-dimensional list of integers from standard input, right? Now just keep in mind that the first thing that these functions expect in standard input is the dimension, right? So when you're using this function, the first number that you need to specify is the number of numbers that are going to be part of this list, which is the dimension, right? And then you list the numbers that are the elements of the list. Same here. You first need to specify the dimension of this 2D list, meaning the number of rows and columns, and then you specify the integers that are part of the 2D list. Okay, and then you have similar functions to read a one-dimensional list of floats and two-dimensional list of floats. So here again, you need to specify the dimensions first on standard input, and then the elements, and then a similar set of functions to read a one-dimensional list of booleans and a two-dimensional list of booleans, right? So that's the API. Now let's look at a client program that makes use of that API to do something very interesting. So this program is called ifs.py, and what it does is it takes a command line argument n as an integer, and then from standard input it's going to read a 1 by m vector of probabilities. So that's going to look something like this. So it's a 1 row by m columns. So 1 row by m columns, and the numbers here are going to be probabilities, right? Meaning each one is going to be a number between 0 and 1. And then the program also reads two m by 3 matrices, all right? So those are going to look something like that. So two matrices that are m rows and 3 columns each. Okay, so that and that, m rows, 3 columns. Okay, so 3 elements here, 3 elements here, and any number of m number of rows, right? Okay, so these are all the inputs. N is a command line argument as an integer, and then these guys, a 1 by m vector of probabilities, and two m by 3 matrices, they are inputs from standard input, right? And then what the program does is it simply plots the results as a set of n points to standard draw. Okay, and how do we figure out the xy points for how do we figure out the xy values for the n points that we want to draw? Well, that is what is done using an iterative process. So we start with an initial value for xy, and then we simply iterate those values n times. Okay, and when we do that iteration, we make use of these inputs, this vector and these two matrices. All right, and since this process is iterative, meaning you start with some initial value for xy and constantly iterate it, it's called an iterated function system, or IFS for short. Okay, so IFS stands for iterated function system, or IFS for short. Okay, so now let's go through the code. Okay, so we import the Std Array Module that we just discussed in the previous slide, and then Std Draw, Std Random, and sys. Okay, and then we the program simply consists of a main function that first reads a command line argument n as an integer, and then it reads this list of probabilities from standard input using the function read float 1d from the Std Array Module. So this function we just discussed in the previous slide. Okay, so using just a single call, read float 1d, you can read this entire list. Okay, and that is read into this variable called dist. So this guy here is dist. Okay, and then we make use of this function read float 2d to read this matrix, and we call that cx. So that's that guy, and then we make use of the same function read float 2d to read this matrix, m by 3 matrix, into the variable cy. So this guy here is cy, right? So with just single function calls, we've managed to read these guys, these lists, right? And then we set the initial value for xy to 0 and 0. All right, and so those are the initial values for xy, which we're going to iterate, right, and draw on the screen. and then we set the pen radius to 0, and then we perform n iterations. So I goes from 0 all the way up to n minus 1, n iterations, right? And then what do we do in each iteration? We get a random number, and notice how we get the random number. We make a call to the discrete function that we talked about from the Std random module. So that's simply going to return an index from this list dist with probability given by dist of I. So this again, recall, is a random number which is index I with probability dist of I. Okay, so it's basically an index from here, so index I with probability dist of I. All right, so that's the probability. Okay, so that's a random index from this list, and then what do? Well, we look at that row from the from these two matrices Cx and Cy. So we take that index R that we get from here, and then simply go to that particular row in these two matrices. So let's say that row was some row here, okay, and some row here. So that's the rth row from these two matrices. Okay, so that's what we're saying here, Cxr, Cyr. Okay, and then notice that both of these guys are m by 3 matrices. So in each of these slices, how many elements are you going to have? 3 elements. Okay, so you have an element there, an element there, an element there, element there, element there, and element there. Okay, so then these two lines are where we calculate new values for x and y. So we say x naught is now the current value of x times this number, okay, and then plus the current value of y times this number plus this number here. All right, so that's x naught, and then y naught is simply the current value of x times this number here. So Cy indexed by r and 0 is this guy. Okay, and then the current value of y times this number, and then this last fellow is basically this guy here. Right? So that's how we compute x naught, y naught, and once we have x naught, y naught, we make that be the new value for x and y. So we say x is simply x naught and y is y naught. So we have managed to iterate x naught and x and y. Okay, it started with some value, it takes on a new value in each iteration calculated by these two statements. All right? Okay, and then once we have the new value for x and y, we simply plot it by saying std draw point xy. Okay, and then at the end of the n iterations, we simply show the canvas on the screen. All right, so that's how the program works. We are constantly iterating the values of x and y using these lists, right? We get a random index from here, go to that particular row in Cx and Cy, and the values that you find in that row are what are used to update the current values of x and y. All right? Okay. So now let's look at some input and output. So what you're seeing here is some input for the IFS program. So this input is stored in a file called serpensky.txt. So the first line that you see there is the dimension of this list. So it's saying that the next thing in the standard input is a list with 3 elements. Okay, so we always need to specify the dimension first if we were to use functions from Std Array to read lists. Okay, so we are saying what follows is a list of 3 elements, and this is that list that we called dist, right? And it contains probabilities, so these guys sum up to 1. And then we have, so this is dist, and then we have a matrix which is m by 3, and in this case m is 3, so it's a 3 by 3 matrix, and this is what we call Cx. So here again we first specify the dimension 3 by 3, and then we specify the matrix itself, the elements. Right? And then finally we have cy, which is also 3 by 3. So we first specify the dimension and then the elements of the matrix. Okay, so that's my input, and then here I run the program ifs.py from the previous slide, giving it 20,000 for n. So I'm saying I want to draw 20,000 points, and I feed this file as standard input to the program, right? And what the program does is it produces this plot, and this is a very famous plot. It's called the Sierpinski triangle, right? And it's also a fractal. So and what is a fractal? A fractal is a self-similar structure, right? So if you zoom into this figure, you will see the same structure repeat over and over again. All right, so the part of the whole resembles the whole, and that's what we call a fractal. Okay, and this is an example of a mathematical fractal where you can zoom in arbitrarily deep, and you will see the same structure emerge over and over again. Right? So Sierpinski triangle is a very famous fractal. Let's look at another example. So here I'm showing you a different file called barnsley.txt, and here dist is a 4-element list. Okay, but it still contains probabilities, so this should sum up to 1. And then cx in this case is a 4 by 3 matrix, and cy is also a 4 by 3 matrix, right? So that's my input in the file called barnsley.txt, and now if I run the same program ifs.py, giving it n as 20,000, and if I give it this file as standard input, the program comes back with this plot. Okay, and this figure here is what is called Bernoulli Function, right? And this is also an example of a fractal, right? Because if you focus on, let's say, this part of the fractal, that resembles the whole. Okay, just like how this part here resembles the whole. Okay, so this is also an example of a fractal. Okay, so IFS is a very interesting program, and you can use the same program to generate or to plot different fractals. All that you need to come up with is a suitable input file. All right. So what we're going to do next is discuss the implementation of the Std Array Module. So this is the third abstraction, right? That's involved in the process of developing a user-defined module. Okay, so this module is called Std Array, and it's a module that defines functions related to creating, reading, and writing 1- and 2-dimensional lists, right? So let's go through the implementation. The very first function in the API was create1d. Okay, so what does create1d do? It creates a list of this size where every element is initialized to this value. Okay, and that value defaults to none, meaning if you don't specify a second argument, every value defaults to none. Right? And the implementation is rather straightforward. What we do is we take this value, okay, as a 1-element list and multiply it by length, the desired dimension. Okay, and that has the end effect of creating a list that has length number of elements, each initialized to value. Right? So for example, if you say create 1d with arguments 5 and let's say 2, what do we get? Well, this return statement is essentially saying the value 2 times the length, which is 5, and this corresponds to a list that has 5 elements, each initialized to 2. Okay, all right, that's that. What about create a 2D? Well, here this function is supposed to create a 2D list that has these many rows and these many columns, and every element is initialized to value, which here again defaults to none. Right? So what we do first is create a list called A, all right, of size row count, where everything is initialized to null. So let's take an example. Let's say this was 2 and this was 3 and the value was 1. right? So what is A going to look like after that first line? Well, it's simply going to be a 2-element list which is none and none. Okay, that's what we get here after this line. And then we say for row in range of row count, so row is going to take on value 0, 1 and so on all the way up to row count minus 1. So in this case row count was 2, so the values for row are going to be 0 and 1. So this is index 0, this is index 1. And then what are we saying? We are saying the row element from A in A is simply this list here. The list containing value multiplied call count times. Right? So what does that do? Well, at the very first iteration, row is going to be 0. So this number, this element here is replaced with a list that contains a call count number of elements, which in this case was 3. And the elements are all set to value, which in this case was 1. So it's going to be 1, 1, 1. Okay, and then in the next iteration row becomes 1, and in that case this element is now replaced with a list that is 1, 1. Okay, so what have we done? We have managed to produce a 2D list whose elements are these 1D lists. Okay. Alright, so that's create 2D, and then finally we simply return A. What about write 1D? So write 1D takes a one-dimensional list as an argument and it's supposed to write it to standard out. We first get its length and then we write the length out. So we write the dimension of that list out so that later on we can use one of the read functions to read this list. Okay. From standard input, right? Okay, and then what do? Well, we walk through that list. So I goes from 0 all the way up to length minus 1, and then we get the element out. So element is A at I, and then we check if this element is a Boolean or not using the isInstance built-in function. So this is going to return true if element is of type Boolean and false otherwise. So if it is not a Boolean, we simply write the element out. Okay. But if it is a Boolean, we check if it is a true or a false, and we write true using as 1 and false as 0. Okay, just to save some space. True elements are not spelled out as true, but just simply written out as 1. Okay, so if the element that you're looking at is a Boolean element, we write 1 for true and 0 for false, and if it is a non-Boolean, we simply write the element out. Okay, and then after we do that, we write a space. Okay, so the values are going to be separated by spaces, and then at the very end we write a new line character outside the loop. Okay, so that's what we do. So if A, for example, is true, true and false, then write 1D is simply going to write it as 1 space 0 followed by a space and then a new line character. What about write 2D? Well, it's not that different from write 1D. So we first get the number of rows by saying a row count is length of A. We get the number of columns by saying length of A at 0. So here we are assuming that A is a non-ragged 2D list. And then we write the dimension out. So we write the number of rows and number of columns separated by space so that we can later on use a read function from this module to read this matrix from standard input. Okay, and then row goes from 0 through row count minus 1, column goes from 0 through column count minus 1. We get the element out by saying element is A at row column, and then here again we do the same thing. We check if this element is a Boolean. If so, we write true elements as 1 and false elements as 0. Okay, and if it's not a Boolean, we write the element out as is, and then we write a space after each element, and then after each row we write a new line character. Okay. So that's how write 2D is implemented. What about read 1D as a list of integers? Well, the first thing that we do is from standard input. Well, actually, even before that, what is this function supposed to do? It's supposed to read a one-dimensional list of integers and return that list. Okay, but for this function to work, it first needs to know how big that list is going to be. So the first thing that it expects from standard input is the dimension of that list, which is what we get here by saying count equals stdio.readInt. Okay, once it knows what the size is, it sets up a list with that size using the create1d function. So create1d count, which is what was read here, and everything is initialized to none to begin with. Okay, and then it simply does count number of iterations, because it knows that it needs to read count number of integers. So I goes from 0 through count -1, and we say a at I is stdio.readInt. So we read each of the integers here from std, and then finally return that list. Okay, so here again, this is very important. This function needs to know how big that list is going to be that it needs to construct. Okay, so it first expects the dimension, and then it sets up a list with that dimension, and then it goes about reading the right number of elements from standard input. Okay, so doing this operation, so saying something like a at I is meaningful only if I is within bounds, right? Only if is valid, only if I is valid, i.e. I is within bounds. Okay, so keep this in mind. Okay, what about read in 2D? Well, here this function is supposed to read a 2D list with m rows and n columns from standard input. So here again, the function first expects the dimension from standard input so that it can set up a list with the right size. So it first reads the row count and column count, and then it sets up a 2D list with those dimensions, right? And every element is initialized to 0. And then we say row goes from 0 through row count -1, and call goes from 0 to call count -1. A at row call is stdio.readInt. So this is where we read each of the elements into that array A, and then finally return that array. Okay. What about read float 1D? Well, this is almost identical to read int 1D. The only difference is here, instead of read int, we say read float. What about read float 2D? It is similar to read int 2D. The only difference is here again, instead of read int, we say read float. Okay? Other than that, it's identical to what we saw before. What about read bool 1D? Well, again, it's the same idea. The only difference is here, where we say read bool instead of read int. And what about read bool 2D? The same idea, except that here we say read bool instead of read int. Okay, and then finally, so we're done with the functions in the API. Finally, we have the test client, and its purpose is to simply test the implementations of the functions in the module, and that's what we're doing here. We are testing the write 2D function and the read float 2D, and then we are testing write 2D again with read bool 2D. Okay, it's a test client. It's private, so it starts with a name that is underscore. All right, at the beginning. Okay, so that completes the implementation of Std Array, a list processing module. The last module that we're going to consider is Std Stats module that you can use for performing standard statistics. All right, and here again we'll follow the 3 abstractions that we talked about, and the first one of which is to look at the API, and that is what is shown here for the Std Stats module. So let's walk through the functions in the API. Mean is a function that you can use to calculate the mean of a list of numbers. Var is a function that you can use to calculate the variance of a list of numbers. Okay, and then stddev is a function that you can use to calculate the standard deviation of a given list of numbers. Median is what you can use to calculate the median of the values in this list A. Now recall that the median is the middle element. Okay, if there is a distinct middle, and if not, it is the average of the two middle elements. Okay, and then there are plotting functions available. So you can use this function plot points to produce a scatter plot of numbers in this list A. You can use this function here to produce a line plot of the numbers in A, and you can use this function to draw a histogram to produce a bar plot of the values in this list A. Okay, so that's the API. So the next thing that we will do is look at a client program that makes use of that API. So this client program is called Bernoulli.py, and what it does is it takes two command line arguments n and trials, okay, and it's going to perform trials experiments, and each experiment involves counting the number of heads that are obtained when a fair coin is flipped n times. So in each experiment we flip a coin n times, a fair coin, and simply count up the number of heads obtained in that experiment, and then we repeat the process trials number of times, and we simply draw the results to to standard draw. All right, so the output is going to look something like this. So let's say n was 10, okay, and trials was 100. So if n was 10, we are interested in how many times did we obtain 0 heads, how many times did we obtain 1 heads, and so on, 2 heads, and so on, all the way up to 10 heads. Okay, so we are interested in this histogram. So that's what the program is going to plot. So how many times did we, out of trials number of experiments, did we end up with 0 heads, 1 heads, and so on, all the way up to 10 heads. Okay, so we import all these modules: Gaussian math, Std array, Std draw, Std random, Std stats, and sys. So these are all modules that we've seen. Okay, and then this is what we do in main. We first get the two command line arguments, n and trials, as integers, and then we set up this one-dimensional array called frequency with size n plus 1. Okay, and this is the array that's going to keep track of the number of heads obtained, right, across all the trials number of experiments. And it is n plus 1 because, for example, when n is 10, we have 11 possibilities for the number of heads, right? 0 heads, 1 heads, and so on, all the way up to 10 heads. So there are 11 possibilities. So we create this array with size n plus 1, everything set to 0. And then we perform the trials number of experiments. So t goes from 0 through trials minus 1, and then we say in each experiment the number of heads is simply std_random.binomial n.5. So recall that binomial flips a coin n times, okay, in this case it's a fair coin, and it reports the number of heads obtained, okay, which we store in heads, and then we simply go to that particular index in frequency. So for example, heads might have come out in this experiment as 5. We go to index 5 and increment that frequency by 1. Okay, so once this for loop is done, frequency has all the frequencies, meaning how many times out of the trials experiments we saw 0 heads, 1 heads, and so on, all the way up to n heads. Okay, and then all that we need to do is some plotting. But before that, we first normalize this array frequency, meaning we turn these numbers into fractions. That's what we're doing. So norm is an array which has the same size as frequency, n plus 1, and then we simply say norm at I is frequency at I divided by trials. Okay, so once this for loop is done, norm is going to have is going to be in fractions. It's the frequency in fraction, right? So that's that. And then we create these two variables, phi and standard dev. So phi is said to be is created as an array of size n plus 1, everything initialized to 0, and standard deviation is simply square root of n divided by 2. Right? So what is this array going to store? Well, this array is going to store the mathematical fit. Right? Norm is what we got for frequency via experiments. Okay, so, whereas phi is going to be the mathematical fit. Right? So it's going to be this curve, whereas norm is going to be these bars. All right? Okay, so we say for I from 0 through n plus 1, fiat I is simply a point obtained from a Gaussian PDF. All right, the ith, the point, the value of the Gaussian PDF at I, and the Gaussian PDF has a mean n over 2 and standard deviation given by that. Why is the mean n over 2? Well, if we flip a coin 10 times, where is this Gaussian curve going to peak? Well, it's going to peak at 5, which is 10 divided by 2, right? If we flip a coin 100 times, right, where is this curve going to peak? It's going to peak around 100 divided by 2, which is 50, right? And hence the mean of the curve is n over 2. And standard deviation, it turns out, is simply square root of n divided by 2. Okay, so that's that. So once this for loop is done, phi has the values of the curve, okay, the idealized curve. And then all that we need to do is make calls to plot these things. So we first set the canvas size to be 1000 by 400, and then we set the y scale to that. So y scale goes from 0 all the way up to the max of norm and the max of phi. Okay, so it's just setting the right y scale, and then we plot norm as simply a histogram, so plot bars, and then we plot phi, the actual curve, using the plot lines function from Std stats. Right? So that's that. So here plot bars and plot lines are functions from Std stats that we discussed in the previous slide. Okay, and finally we simply show the canvas. All right, so let's look at some input and output. So here we run that program, that client program Bernoulli.py, with n set to 20 and trials set to 100,000, right? So we're saying perform 100,000 experiments where each experiment involves flipping a coin 20 times, right? So this is the output that we see. So on the x-axis, what do we have? Well, we have 0, 1, 2, 3, and so on, all the way up to 10 here, and then 11, 12, and so on, all the way up to 20. And what you see here are simply the number of heads obtained, all right? And notice that the curve peaks around 10 because n was 20 here, right? And what you see here as this line is the mathematical fit. So that's a Gaussian curve, a bell curve, whose mean is 10 in this case, right? And then what you see as bars are what we got from experiments, right? And since we repeated this experiment 100,000 times, we got a pretty good fit, right? So the curve very nicely fits the experimental data, which are given by these bars, right? That's a nice little client program that makes use of the Std stats module. So the last bit for this lecture is to talk about how we implement the Std stats module. And that's what you see here. So Std stats .py is a module that defines functions related to statistical analysis and graphical data display. And here is the implementation. So the first function in the API was mean, and that simply calculates the mean of this list of numbers, and the implementation is straightforward. We simply return the sum of the elements in A divided by the number of elements in A. What about the variance? Well, this implements the standard formula for variance. So we first calculate the mean of this list of numbers by making a call to this function here, and then we say total, we set total to 0, and then we iterate through the values in A and update total as total equals total plus x minus mu times x minus mu. Okay, and then finally we simply return the total divided by the length of a minus 1, and that's the formula, standard formula for variance. So let me write that down here. So variance of a list of numbers, so if a is the list x1, x2 and so on all the way up to xn, and if the mean is mu, then the variance is simply calculated as x1 minus mu the whole square plus x2 minus mu the whole square and so on, plus xn minus mu the whole square, the whole thing divided by n minus 1. Right? That's the standard formula for variance. That's what we're calculating here. And then standard deviation is straightforward. So standard deviation is simply the square root of variance. Right? That's what we do. So we say mat dot square root of the variance of the given list. And how do we calculate variance? By making a call to this function. What about median? Well, we are given a list A and we want to find the middle element. So the first thing to do is to sort that list A, right? But the way we do that is by making a call to the sorted built-in function that takes the given list as an argument, okay, and it returns a sorted copy of that list. It doesn't modify A. That's very important, right? We don't want to modify A in the process of calculating the median. So we simply call the built-in function sorted to sort A and return the sorted copy as a return value without modifying A itself. Okay, and then we simply get the length of that list here, and then we check if that list has an even number of elements or not. If it has an odd number of elements, then it has a distinct middle element which is given by the index length divided by 2. So we simply return the value at that index. So this is when we have an odd length. And here is even. So if the length of the input list is even, we don't have a distinct middle. So what we do is we simply return the average of the two middle values. So we go to index length over 2 minus 1 and get that value out. And then we go to the index length that divided by 2 and get that value out. And then we calculate the median as the average of those two numbers. So it's that plus that divided by 2. Okay, so that's how you calculate the median of a list of numbers. The next set of functions are the plotting functions. So here plot points takes a list of numbers A as an argument, and it's supposed to plot the points in that list. So we first get the length out, and then we set the x scale to go from -1 to n, and then we set the pen radius to be that. It's simply scaled by the number of points. And then we do a loop, a simple loop that goes from 0 through n minus 1, and for each in each iteration we simply plot the point whose x coordinate is I and y coordinate is given by the value in A at index I. All right, so that's what we are doing. So this is the x coordinate and that's the y coordinate. All right, so that's plot points. What about plot lines? So here we are given a list and we are supposed to produce a line plot, right? So we first get the length of the list, set the scale, x scale to be from -1 to n, and then we set the pen radius to 0, and then we have a loop that goes from 1 through n minus 1. And what are we doing here? We are making a call to the function line from std_draw, and we are simply connecting the ith point to the I minus 1th point. All right, so we are looking at a point I, so that's I, whose y coordinate is A at I, and we are connecting that to the point, let's say I minus 1, whose y coordinate is A at I minus 1. Okay, so we are simply connecting these 2 points, and then I marches ahead, we connect the next point with this one, the next point with that one, next point with that one, and so on, right? So we end up producing a line plot. What about plot bars? So here we are supposed to draw a histogram. So we are given a list A, we first get its length, and then the x scale goes from -1 to n, and then we say for I in range n, so I goes from 0 through n minus 1, we simply draw a filled rectangle with these arguments. Right? So I minus 0.25, 0, 0.5, and 8i. All right. So what we are doing here is for each each value of I, we are simply drawing a filled rectangle. Right. So that's what we do. So the next value of I, draw another filled rectangle, draw another filled rectangle, and so on. Okay. Okay, and then finally we have the test client. Again, its purpose is just to test the functions in the module. So it's a private function, so its name starts with an underscore, right? And here we're simply getting some data from standard input as a one-dimensional array of floats, and we simply calculate its mean, its standard deviation, and its median, and print it out. So we're basically testing these functions in the module. All right. So that completes the implementation of standard stats module, and that also concludes this lecture on modules and clients. Thanks for your time.